Hello friends, in the part first of the ultraviolet and visible spectroscopy, we have seen the range as well as sources of ultraviolet and visible radiation, principle of the ultraviolet and visible spectroscopy, and Beer-Lambert's law. In the principle, we have learned why this ultraviolet visible spectroscopy is called as a electronic spectroscopy. Therefore, in connection with that, in this part, we will see the electronic transitions. So the first point is the allowed electronic transition sigma to sigma star, pi to pi star, n to sigma star, and n to pi star. These transitions are allowed electronic transitions. The second point is a forbidden electronic transition, that is sigma to pi star and pi to sigma star. And third point that we are going to discuss here, it is the selection rule for transition. Delta S is equal to 0, delta L is equal to plus minus 1, and symmetry. On the basis of selection rule, we can decide whether the electronic transition is allowed or forbidden. So these points we will discuss in this video. So let's start with the electronic transitions and their types. There are different types of electronic transitions occurs in a molecule or a compound when the ultraviolet and visible radiation is passed to the solution of the compound. These electronic transitions are divided into three types. The first type is N to V transition, second is the N to Q transition, and third type is N to R transition. To understand this N to V, N to Q, or N to R transition, we have to know the bonding orbitals, non-bonding orbitals, and anti-bonding orbitals and their energy level. So the energy level diagram for different bonding, non-bonding as well as anti-bonding orbital is drawn here. Now from this diagram we can say that the sigma bonding orbital is having a low energy and sigma star anti-bonding orbital is having higher energy. Now the N to V transition, it means that the electron is promoted from a bonding orbital to the anti-bonding orbital. Now we have a two bonding orbital as well as a two anti-bonding orbital. Therefore, electron it can be promoted from sigma bonding orbital or pi bonding orbital to sigma star antibonding orbital or pi star antibonding orbital. Therefore, we have here N to V transitions such as sigma to sigma star, pi to pi star. In addition to this, we have a sigma to pi star and pi to sigma star. So these four transitions, they are called as a N to V transition in which electron is promoted from bonding orbital to anti-bonding orbital. Out of these four transitions, these first two are, that is sigma to sigma star and pi to pi star. These transitions are allowed transition, whereas these two transitions, that is sigma to pi star and pi to sigma star, these are forbidden transition. Why these are forbidden and why these are allowed transition, that we are going to discuss in the last part. Now the second transition is, that is N to Q transition. In N to Q transition, electron promoted from non-bonding to anti-bonding orbital. As there is one non-bonding orbital and two anti-bonding orbitals, we have here either electron is promoted from non-bonding to sigma star, that is antibonding orbital, or non-bonding to pi star antibonding orbital. So in N to Q transition we got N to sigma star or N to pi star transition. Now the last one is N to R transition. Here the electron is promoted from ground state to a state where it is having more energy, highest energy, and it causes the ionization of the molecule. So this transition of the electron causes the ionization of the molecule. So from this discussion, it is clear that there are a 6 transition, out of which 4 are allowed transition and 2 are forbidden transition. In this diagram, you can see here sigma to sigma star and pi to pi star. Electron is promoted from this sigma to sigma star antibonding, pi to pi star antibonding. Then in this here there is a sigma to pi star and pi to sigma star. These two transitions, they are forbidden transitions. And lastly, n to sigma star and n to pi star, these are allowed transitions. So the 6 transitions are occurring in the compound when it is interacted with the ultraviolet and visible radiation, but out of which 2 are forbidden and 4 are allowed. Now we will see one by one in which compounds the transitions, that is sigma to sigma star or pi to pi star or n to sigma star or n to pi star, in which compounds they are appears, and what is the wavelength and what are the molar absorptivity epsilon max for that transitions. So let's start with the sigma to sigma star transition. Sigma to sigma star transition, it is one of the n to v transition where the electron from the sigma bonding orbitals are promoted to the sigma star anti-bonding orbital. And in the energy diagram, we have seen that the energy difference between here sigma bonding orbital and sigma star anti-bonding orbital is very much high. Therefore, here the delta E, I will write here, it is high, as the energy required for the promotion or transition of the sigma electron from bonding orbital to the anti-bonding orbital is high. The wavelength, that is lambda max, here it is found to be around 150 nanometer. I will write here a range that is 120 nanometer to 200 nanometer. So below 200 nanometer we get a wavelength. That's why this transition is observed in a far ultraviolet region, and it is giving only the information about the single bond. Then for this transition, the epsilon max, that is molar absorptivity, is found to be 1000 up to 10,000. Now example for this sigma to sigma star transition is, this transition is observed in a saturated compounds only where there is a single bond, that is sigma bond. So we can write the examples of alkanes. So here I will write a methane, ethane, this type of compound, they shows sigma to sigma star transition. And here the energy required is very much high, lambda max is less as compared to other transition. Now the second transition from n to v, it is the pi to pi star transition. Here the pi electron from pi bonding orbitals are promoted to pi star anti-bonding orbitals, and the energy required for the transition is less than that of sigma to sigma star transition. Here, as the energy required is less, here the lambda max, that is the wavelength, is around 200 nanometer up to 700 nanometer. It depends upon the structure. So when there is a more number of multiple bonds in a compound, then the lambda max shifted towards 700 nanometers. Here molar absorptivity, that is epsilon max, is found to be once again 1000 up to 10,000. And the example for this pi to pi star transitions are the compounds containing multiple bond. or we call it as a unsaturated compound. So it may contains carbon double bond carbon, carbon triple bond carbon, carbon double bond nitrogen, carbon double bond sulfur, carbon double bond oxygen, this type of compound. So it may be a ethylene, that is alkene, alkyne, or nitro compounds, that is azo, then imines, then thiocarbonyl compounds or carbonyl compound. They shows pi to pi star transition. Now the third transition is belongs to the N to Q transition, and it is transition of the electron from non-bonding orbital to the sigma star antibonding orbital, that is N to sigma star transition. It is observed in case of methanol, and here you can see the lone pair present on the oxygen. From that lone pair, one electron is promoted up to antibonding orbital, that is sigma star, and here the energy required for the promotion of the electron is less than sigma to sigma star transition, but it is more than pi to pi star transition. So more energy is required than pi to pi star transition. Therefore, the wavelength for this transition required is in between sigma to sigma star transition and pi to pi star transition, and we can write here the range, that is 150 nanometer up to 250 nanometer. This is the range where we can observe N to sigma star transition. Here molar absorptivity, that is epsilon max, is 100 up to 3000. This type of epsilon max is observed, and the example that are showing the N to sigma star transitions are the compound containing heteroatom and a single bond. So we can write the compound having this type of functionality, that is carbon is attached to the oxygen, carbon is attached to the nitrogen, carbon is attached to the sulfur, or carbon is attached to the halogen. This type of functionality, if present in a compound, they definitely show N to sigma star transition, because this heteroatom, that is oxygen, nitrogen, sulfur, or halogen, they have a lone pair. The fourth transition, it is N to pi star transition. Against non-bonding electrons, they are promoted from non-bonding orbital to the pi star antibonding orbital. It is N to Q type of transition. Here the example of acetone is taken, where the lone pair on the oxygen, out of which one electron is promoted from non-bonding orbital to the pi star antibonding orbital. Now for this transition, energy required is less than any other transition. So as energy required, that is delta, is very much less, the lambda max for this transition is high, and it is about 200 nanometer up to 700 nanometer. But the epsilon max or molar absorptivity or the intensity of the peak or a signal in the UV spectrum, which is given by the epsilon max, is very much less. So here we found epsilon max up to uh, 10 to 100. In this way, the N to pi star transition require less energy and more wavelength. The example for N to pi star transition, the compounds which are having a unsaturated bond as well as presence of heteroatom, they definitely shows N to pi star transition. So the compound, that is carbon double bond oxygen, that is carbonyl compound, that is imine compound, or a skip bases, they shows this type of N to pi star transitions. So another, I will write C double bond S, then cyanide C triple bond N. These are the example of compounds showing N to pi star transition. Now see the spectra of acetone. Here you can see the acetone is having structure, that is CH3COCH3. It contains a non-bonding electron as well as pi electron as well as sigma electron. So in this compound, all the four transition, that is sigma to sigma star, then pi to pi star, then n to sigma star as well as n to pi star transitions are possible. But this sigma to sigma star transition is obtained below 200 nanometer, around 150 nanometer. This pi to pi star transition is observed at a lambda max, that is 195 nanometer, which is showing here, and it is having more intensity, that is epsilon max is very high. Then n to sigma star transition, it is below 200, around 150. So I will write here below 200 nanometer. And n to pi star transition, it is observed at 274 nanometer, but the epsilon max is very much less. In this way, we can have four different type of uh, allowed electronic transition, that is sigma to sigma star, pi to pi star, n to sigma star, and n to pi star. And if we compare the energies required for these transitions, then we can write here the sequence, that is sigma to sigma star transition, they requires more energy than that of n to sigma star transition, than pi to pi star transition, than n to pi star transition. So in this way, sigma to sigma star transition requires more energy, whereas n to pi star transition require less energy. And when we compare the wavelength, then the wavelength, that is lambda max, on this side it is less, on this side the lambda max is high. So we can compare the wavelength as well as energy of this transition. The selection rules for transition. In this selection rule, we will see the first rule, that is delta S is equal to 0. Second, that is delta L is equal to plus minus 1. And the third rule, that is symmetry. These rules are used to check whether the transition, that is electronic transitions, are allowed or forbidden. So the first rule is delta S is equal to 0. It belongs to the spin quantum number. Consider this sigma orbital or this pi orbital. When the electrons from this orbital, they are promoted to sigma star, or from this orbital to pi star, then what happens? If the spin, here I have written, so I will write once again. If the spin of this sigma electron or pi electron remains same after promotion, so it is in the upward direction. If it remains in upward direction in both cases, then the spin after promotion is same. That's why delta S is equal to 0. If the spin after promotion changes, that is it becomes in a downward direction, then delta S is not equal to 0. In such case, if the spin is changed, then the transition is forbidden. And if delta S is equal to 0, the transition is allowed. All type of transitions are allowed according to this delta S is equal to 0. Then the second rule, that is a delta L is equal to plus minus 1. To understand this rule, we have to consider the azimuthal quantum number. I will write here azimuthal quantum number, and the values of azimuthal quantum number for s orbital, it is equal to 0, for p orbital it is equal to 1, for d orbital it is equal to 2, and for f orbital it is equal to 3. Now when electron is promoted from s orbital to p orbital, then what is happening? The delta L becomes 1 minus 0, that is 1 minus 0 is equal to 1. For transition of the electron from p orbital to d orbital, again delta L is equal to 2 minus 1 is equal to 1. But when the electron is promoted from s orbital to d orbital, Then in this case, a delta L is equal to 2 minus 0, it is equal to 2. Therefore, when the values increases beyond plus minus 1, then that transition is not allowed. It is the forbidden transition. So the transition is allowed only when it is occurs S to P, P to D, or D to F, or vice versa. If F to D, then it is okay because minus 1 is there, delta L is equal to minus 1. Now the third rule which is used to identify the sigma to pi star transition as well as pi to sigma star transition, why they are forbidden. So by using third rule, that is symmetry rule. So I will write here a symmetry. For that purpose, just here consider the structure of this atomic orbital. Now here these two lobes are joined together. This is the center point. From this center point, the equal distance is there at which the lobes are present. So this sigma orbital possesses center of symmetry. So I will write here a sigma orbital possesses a center of symmetry. Now for uh, pi orbital, when we consider pi orbital, if we take this point as a center, from this point, this is the first lobe, then on this side, this is the second lobe. These are unequal because here it possesses pi electron, but it is empty orbital. So it doesn't have a center of symmetry. So pi orbital, no center of symmetry, I will write. Then consider a pi star as well as sigma star. For pi star orbital, here I will erase this electron, so you can get this is the center from this, and so these two lobes are same, these two lobes are same. So pi star orbital, it also possesses center of symmetry. But when we consider, so first of all I will erase this electron, then this is the center, and from this side and from this side I will draw the lines, and these are the two lobes, they are different ones. So sigma star orbital, it doesn't possesses center of symmetry. When the orbital possesses center of symmetry, that orbital it is called as a zirad. If the orbital doesn't possess a center of symmetry, that orbital is called as a unzirad. So in this way, the sigma and pi star, they are zirad, and pi and sigma star, they are unzirad. Now the rule is there where it is said that when the promotion of the electron is occurs in such a way that zirad to unzirad, that is Z to U or U to Z, then these transitions are allowed transitions. And if the transitions of the electron occurs from zirad to zirad or unzirad to unzirad, these transitions are forbidden. So I will write here, these are the allowed transition, these are the forbidden transition. Now consider the sigma to pi star transition and pi to sigma star transition. Here sigma is zirad and pi star is zirad. So zirad to zirad, it is the forbidden. Then pi to sigma star, pi is unzirad and sigma star is unzirad. So it is again a forbidden transition. Now consider a sigma to sigma star transition. Sigma is zirad whereas sigma star is unzirad. So it is the allowed transition. Therefore, sigma to sigma star, pi to pi star, n to sigma star, and n to pi star, these are allowed transition, whereas these two transitions, that is uh, sigma to pi star and pi to sigma star, they are forbidden transition according to the symmetry selection rule for transition. Though they are forbidden, they shows a lambda max as well as epsilon, but the intensity is very much less, so that we cannot detect that transitions. So this is about the selection rule of transition, and here we will stop. In this video, we have gone through a selection rule as well as allowed and forbidden transitions. In the next video, we will see the effect of conjugation on the ultraviolet band and intensity of the band.